welcome to Two Projects. In this video, we are going to explain the project Epileptic Seizures Prediction using Deep Learning. Introduction. This project aims to utilize deep learning techniques for the prediction of epileptic seizures. By leveraging advanced neural network architectures, we seek to develop models capable of accurately forecasting the onset of seizures in individuals with epilepsy. Epilepsy is a neurological disorder characterized by recurrent seizures, often with unpredictable timing and severity. Predicting seizures in advance can significantly improve the quality of life for patients by enabling timely interventions, reducing the risk of injury, and providing peace of mind for both patients and caregivers. The ability to anticipate seizures also offers opportunities for personalized treatment approaches, ultimately leading to better management of the condition. So, patients, caregivers, and healthcare providers benefit from precise EEG state prediction, fostering better diagnosis, treatment, and support. Improved understanding of brain activity enhances treatment outcomes and ensures personalized care for individuals with epilepsy and neurological conditions. And deep learning models, notably CNNs and RNNs, play a pivotal role in extracting intricate EEG patterns, enabling accurate prediction of seizure activity and brain states. These models facilitate real time monitoring, localization of abnormalities, and informed clinical decision making for better patient outcomes. Objective of the project. So, as I mentioned earlier, the primary aim of the project is to design and implement a robust diagnostic system utilizing deep learning techniques. This system will accurately analyze EEG data to aid in the diagnosis of epilepsy, including the identification of seizure activity, tumor affected brain regions, and variations associated with different brain states. And the project seeks to enhance diagnostic accuracy by leveraging advanced deep learning models, including RNN, LSTM, and combination of CNN and LSTM architectures. These models will extract meaningful patterns from EEG signals, enabling precise detection and localization of epileptic activity. And by developing a reliable diagnostic system, the project aims to provide healthcare professionals with valuable insights for epilepsy diagnosis and treatment planning. The system will support timely interventions, personalized patient care, and improved management of epilepsy, ultimately enhancing patient outcomes and quality of life. Requirements needed to execute this project are software requirements. Software needed is Anaconda. Primary language used is Python. Front-end framework used is Flask. Backend framework used is Jupyter Notebook. Database used is SQLite 3. And front-end technologies used are HTML, CSS, JavaScript, and Bootstrap 4. Hardware requirements needed are operating system of Windows, processor of i5 and above, RAM of 8 GB and above, and hard disk of 25 GB and above. Now we'll discuss the working models of law of work. So the first step is importing required packages. In this step, we import essential Python libraries such as NumPy, Pandas, sklearn, TensorFlow, Keras, Matplotlib, and Seaborn. These libraries provide functionalities for data manipulation, visualization, machine learning model development, and evaluation. The second step is exploring the dataset. Here we conduct exploratory data analysis to gain insights into the dataset structure, distributions, and characteristics. We examine features, identify missing values, and explore relationships between variables to inform subsequent pre-processing steps. The third step is visualization. Visualization plays a crucial role in understanding the data. We create count graphs to visualize the distribution of target classes, providing insights into class balance or imbalance. Additionally, we generate time versus amplitude graphs to visualize EEG signals, enabling us to identify patterns and anomalies. The next step is data pre-processing. So, data pre-processing involves tasks such as encoding categorical variables, handling missing values, and scaling features. Here, we use label binderizer to encode categorical target variables into binary format, ensuring compatibility with machine learning algorithms. The next step is train and test split. Here, we split the dataset into training and testing sets to assess model performance on unseen data. This step ensures that our model generalizes well to new observations, helping to avoid overfitting. The next step is training and building the model. In this step, we train deep learning models including LSTM, RNN, and combination of CNN and LSTM architectures using the training data. These models learn to extract relevant features from EEG signals and predict distinct EEG states. The next step is performance comparison. Here, we evaluate model performance using metrics such as accuracy, precision, recall, and F1 score on the test data. This step enables us to compare the effectiveness of different models in accurately predicting EEG states, guiding the selection of the best performing model for deployment. And in the next step, we develop a user friendly front end using Flask to provide an interface for inputting test data and displaying prediction results. This front end facilitates interaction with the diagnostic system, enhancing usability and accessibility. So, after signing in, users input test EEG data into the front end interface, which is then pre processed by the developed model for prediction. The system accepts EEG signals in the desired format, ensuring compatibility with the trained models. And the system predicts distinct EEG states, including seizure activity, tumor affected brain regions, and variations due to eyes open or closed, based on the input test data. Users receive the prediction results, enabling informed decision making in epilepsy diagnosis and treatment planning. Now we'll understand about the algorithms used. So the first algorithm built is combination of CNN and LSTM. So, the CNN plus LSTM architecture combines the strengths of convolutional neural networks and long short term memory networks to effectively analyze sequential data such as EEG signals. CNNs excel at capturing spatial patterns in data, making them suitable for extracting relevant features from the raw EEG signals. These features are then fed into LSTM layers, which are adept at capturing temporal dependencies and long range dependencies in sequential data. This combination allows the model to learn both spatial and temporal patterns in EEG signals, enabling accurate prediction of distinct EEG states, including seizure activity, tumor affected brain regions, and variations due to eyes open or closed, making it well suited for this project. The next algorithm built is LSTM, that is long short term memory. So, LSTM is a type of recurrent neural network architecture specifically designed to address the vanishing gradient problem and capture long term dependencies in sequential data. So, LSTM networks utilize memory cell, gate mechanisms, and input and output gates to regulate the flow of information through time steps. This enables them to retain important information over long sequences, making them well suited for modeling temporal dependencies in EEG signals. In this project, LSTM is chosen for its ability to effectively capture complex patterns and temporal relationships in EEG data, allowing for accurate prediction of distinct EEG states associated with epilepsy diagnosis. And the next one is RNN, that is recurrent neural network. So RNNs are specialized deep learning models adept at analyzing sequential data like EEG signals. With connections looping back on themselves, RNNs maintain memory of past inputs, enabling them to capture temporal dependencies and learn patterns over time. This capability makes them ideal for understanding the dynamic nature of EEG signals and predicting distant states such as seizure activity or variations due to eyes open or closed, crucial for accurate epilepsy diagnosis and prediction. Now we'll see the comparison graphs. So this is the bar graph comparing accuracy scores of different algorithms. In this graph on x-axis, I have algorithm names and on y-axis I have accuracy scores. Accuracy measures the overall correctness of predictions, showing the percentage of correctly classified instances. This is precision scores comparison graph. In this graph on x-axis, I have algorithm names and on y-axis, I have precision scores. Precision measures the accuracy of positive predictions, indicating how many predicted positives were actually correct. This is recall scores comparison graph. In this graph on x-axis, I have algorithm names and on y-axis, I have recall scores. Recall measures the ability to identify all relevant instances, showing how many actual positives were correctly predicted. And this is F1 scores comparison graph. In this graph on x-axis, I have algorithm names, and on y-axis, I have F1 scores. F1 score combines precision and recall into a single metric, balancing accuracy and completeness in predictions. So the algorithm which is best performing in all the performance metrics will be used for classifications, and we can see the combination of CNN and LSTM is doing well. Execution of the project. To execute this project, first we need to open the code folder which contains the project source code files. So this is dataset folder in which I have required epileptic seizure recognition dataset on which we'll train the models. And this is test data which contains the test cases on which we'll make the predictions. This is models folder which contains model files which contain algorithm information. These files will be loaded into the project code during runtime to utilize the trained models. This is static folder. This folder consists of files related to CSS, JavaScript, and Bootstrap. This is templates folder. This folder contains all the HTML pages used in the project. It typically includes files like index.html, about.html, etc., which represent different pages of the website. This is app.py file. This .py file contains the information related to front-end logic. It includes coded in Python that handles server-side operations such as processing user requests, interacting with the database, and generating dynamic content to be rendered in the HTML pages. This is Notebook Jupyter source file which contains a combination of code, graphs, and outputs all in one place. It allows users to write and execute code in individual cells, making it a popular choice for data science. And this is signup.db file. This file is the database file used to store user information. So now copy the path of the code folder from the address bar of the file explorer. I'm copying it. Open Anaconda prompt. So now use the command cd followed by a space and paste the copied path and hit the enter button. So this command is used to change the current directory to the code folder's path. Now compile the app.py file using the command python space app.py. I'm typing python space app.py and hit the enter button. So this command will execute the Python script and perform a runtime check for any syntax errors or logical issues. After running the app.py file, the Flask framework will host the application locally at the default address, localhost, and port unless configured differently. Now copy the local link provided by the framework. I'm copying it and paste it into any web browser. I prefer Chrome. After pasting it, hit the enter button. So the home page of the project has been displayed in the browser. This is the front end built using Flask framework. So here we can see a login link, click on it. So here we have to provide a credentials, username and password to sign in. And if you are new to the system, we have to register first. Click on sign up button, fill in all these details and click on register button to sign up. So as I'm already a member, I'm clicking on the sign in link. I'm giving my credentials here and click on login button. So it has redirected us to the classification page. So now we have to upload the test cases to identify the seizure activity, tumor affected brain regions, and variations associated with different brain states. Click on choose file button. So we'll upload the test data which contains the test cases. Click on open button. So we can see the test data has been loaded. Now click on upload button. So these are all the test cases we have, and here we can see the predicted label, that is eyes open, which means during the EEG recording session, the patient's eyes were open. Eyes closed means during the EEG recording session, the patient's eyes were closed. And similarly, we have other labels like recording of seizure activity. So these predictions of seizure activity and variations in brain states like eyes open or closed during EEG recordings aid in early warning, treatment planning, research, and personalized medicine for neurological disorders. So in this way, we can upload the test data and can get the predicted labels. Now click on sign out. So the conclusion here is In this project, we aim to leverage deep learning techniques for the accurate prediction of distinct EEG states associated with epilepsy diagnosis. By analyzing EEG patterns, including seizure activity, tumor affected brain regions, and variations due to eyes open or closed, our goal was to develop a robust diagnostic system to aid in epilepsy diagnosis and treatment planning. The motivation behind this project stemmed from the need for precise neurological assessments and personalized patient management in epilepsy and neurology. By harnessing the power of deep learning, we aim to enhance diagnostic accuracy and provide valuable insights for healthcare professionals to optimize treatment strategies. So, we built and evaluated several deep learning models, including recurrent neural networks, long short term memory networks, and the combined CNN and LSTM architectures. While all models showed promising performance, the combination of CNN and LSTM architecture emerged as the best performing model, demonstrating superior accuracy, precision, recall, and F1 score in predicting EEG states. So, the combination of CNN and LSTM model selected as the best performing algorithm has been deployed in Flask to provide a user friendly interface for epilepsy diagnosis. Users can input EEG data through the interface and receive predictions for distinct EEG states, facilitating informed decision making by healthcare professionals and personalized patient care. So, the implementation of the combination CNN and LSTM diagnostic system holds significant implications for patients, caregivers, and healthcare providers in epilepsy and neurology. By enabling accurate epilepsy diagnosis, localization of brain abnormalities, and understanding of brain responses under different conditions, this project enhances patient outcomes, treatment efficacy, and overall quality of life.
Thank you for watching video. For more projects, please visit our website www.trueprojects.in. For updates on latest project videos, please visit True Projects YouTube channel and subscribe.